such that the polynomial best fits to all these points. And again, there are, like, if you do too much, you will end up with variance, and if your polynomial is too much constraint, doesn't have identity, then you end up with bias. So that's what, like, bias and variance. So that is one perspective where you see that machine learning is nothing but curve fitting, as simple as it. But if you look from other perspectives, machine learning could be like, you don't solve the problems in this machine learning in this in a certain space. So your input space, you just go to a latent space. That is what your hidden layer. So a hidden layer 1, 2, 3, 4, those are nothing but migration of your data or representation from one space to the other and keep on moving. So ideally, what you prefer for it is you have a limited input space where you can't classify them. What you do is you just take this input space, project it into a higher dimension. This is not new because somebody who is good in communications, they know that, like, your coding algorithms, what they do is they just multiply it to polynomial. So from your input space, which is limited with dimension, they go to higher dimension, and then in the higher dimension you can visualize them better and try to have an hyperplane which can separate things out. Okay? So this is something like, you can say, neural network or machine learning is linear and non-linear transforms from space and try to map and then try to separate out and make a classification. That is another perspective. If you want to add maybe one more, you can think about machine learning as something like a generalized program. You start with a program. Say, suppose if I give you a task and say that there is something to be done, computer science engineer, forget about machine learning algorithms. If they are asked, they will be trying to say that they will write a program, a very specific program, which will try to attack the data set using something like data structures and algorithms. They come up saying that I have written a program where you try to feed in input and it is going to give accordingly output. So we are going to solve. But in ML, what you are going to do is you are not taking the knowledge of your data structures and everything. What you say is, I start with a generalized program. I can say my neural network is a generalized program, and I allow this program to self-optimize and come up with trying to solve this problem. Solve the problem. So what is the advantage you see that is if you had a problem which was to be solved by a computer science engineer with data science, other things, structures, so where it requires a lot of domain knowledge in that space. But here you are trying to take a generalized program, and this program is nothing but saying that I have n cross m layers and something. It's very simple. Anybody can do it, and you don't require skill set or knowledge of maybe it's too much optimistic, but you can still solve that problem by just asking the network to say that tune it to yourself. So you have a program which tunes to yourself and solves it. And here you are trying to take out the dependency of programming from the computer science engineer. So this is actually a plus point for somebody else who is not in computer science, because you're not relying on computer science engineer. Even any engineers with minimum knowledge in something like coding, like Python or handling neural networks, can solve the same problems without learning data structures. So you can see it that way, like machine learning enables this. Okay. There could be like a few more perspectives, but I limit with it, so you can take that. Now we talk about like how big today's AI. I think justification is like we can see from recent past. There are many UG programs, specialized programs open. This itself says that, like you had like a telecom revolution a few years back, decades back. Now you have something like AI revolution, which just opens up. So is this the peak of it? Probably not, because this is just, it looks like it is just a beginning. So if somebody thought that, okay, we have an IBM which can store something like some MB of it within this room, but that was 50 years back. And if they thought that this is the optimum of storage on computer science, probably it will not. When the field grows is when people start using, common people start using AI for day-to-day applications, which means it is still yet to come to us, if you agree, because you may think that AI is there, but AI algorithms are there, or the systems which run in the cloud, which run in the GPU. Not AI systems are not still yet. Maybe you can argue that they are a bit in something like cell phones, but that is limited. Okay, so when the real AI development, you can see that when people start using and it is available, the computation happens with your devices, not when it is cloud connected, not it is run with a GPU or heavy machines like Intel i9 or something. So, but the challenge is how do you bring all those AI applications, which requires enormous amount of, if you look here, I just concentrate on this. If you look here, this x-axis, it says that we have a neural network which attacked this problem. So if you look at ImageNet, is a data set, probably something around 14 million images, and it has to classify, given the image, it has to classify whether this object belongs to one node of the 100,000 objects. So the objects could be plane, dog, cat, whatever. You give like any of the image in that 14 million size data set, it has to classify. It was actually a challenge which started like very years back. Then in the beginning, we had networks with a limited number of accuracy. So as you progress, we have seen that there are networks which have been developed providing higher accuracy as possible. So maybe this is not the state of art, but it says that to some extent, like we had inception net and exception, this providing an accuracy of around 80s. But the thing is, like what it takes to improve this accuracy is from the small size, where the number of parameters, this circle represents this size. You can just refer for it. So each of these is, maybe this is something like 2 million parameters. But if you look at this size, probably this one, this is 32 million parameter. ResNet 101 is 44 million parameters. And when you say parameter, each parameter is 32 bit. So 44 million into 32 bit. Think about the storage one. So it takes, like, even if you want to have, like it says that you just have to have your complete hard disk, and that where the model occupies and it tries to solve. So the growing size of your model is something which requires storage capacity. The other is like, so where are we now in terms of catching up this? So before 2020, that is before, prior to COVID, we can see that there are introduction of this transformers, BERT, for all these NLP NLP algorithms. Then we have this ChatGPT, then Megatron, and so on. But somewhere here you see that earlier what we had is we had a hardware which was able to have this, support this, all these models. Why? Because not just because you are AI good. Nobody thought that okay, the BERT model will come and we have to make it ready. This thing, like your GPUs were ready to run this because these were designed not taking into picture this AI. It was designed to take into picture the gaming. Gaming, you can say something like this thing, cryptography, that is minting crypto coins, etc. So taking that into account, the hardware was ready. But the thing is, AI took this opportunity, these models, and started using GPU available here comfortably. But after 2020, you can see there is a challenge. Now we are talking about size of the number of size parameters. You can say 175 billion. This is 530 billion. And do we have the GPU to support it? Of course not. You can say A100 can have here and up to 80 GB. So we don't have facility enough with the GPUs where this huge, because data scientists, what they give is just another line or another for loop, just add layers together. Adding layers together is fine, but if you ask an engineer, is it that easy to bring a more number of hardware parallel operations into your chip? Experience says it is not. Okay, so it's not difficult. It's difficult. You can see that this is more like a steady, but this is more like increasing. You can say linearly or exponential. Yeah, this is exponential because this is log scale. So the challenge is how do you bridge this gap? Are you going to scale up your GPU saying that accommodate everything, or you are going to use some smart techniques to say that let us fill this gap by using some better options? And other thing is like, what are we want to address? We want to address these challenges, not something like what do they demand. You can see here, roughly, this is your autonomous driving car, right? So where you have, this guy has left the hand which says that it has to drive on its own. And what you are trying to take as an input for this is all nothing but your LiDAR, radar data, or if it is camera based, then vision images also. So that will be processed at maybe 30 frames per second. So think about the complexity of the input coming in and the redundancy, or the when you want to make a path prediction, what is the amount of data that you have to process it. So some study says that you would have heard of EV vehicles, and if the EV vehicle is used for autonomous navigation, then probably the power consumption is not because of the motors that is being attached to the wheels. The major power component for your EV, if it is autonomous, is for path prediction. What has to be the next step taken by your vehicle? So predicting that path based on your inputs, what you're considering. That itself is taking large amount of power. It's not your motors, DC motors or whatever. So that's a challenge. And if you can see here, a robot or surveillance, this is something like picture to text and then again generating a picture out of it. This is more like a translation, okay, from one language to other. So if you want to do it, probably it requires cloud computation and it is not efficient, and something we may not able to take it always granted that cloud is available. And don't think about option of taking GPU. You may think that, okay, what is the problem? I can take the huge model and put it in a memory card. Maybe it could be magnetic or even like statograms and so on, SD cards. And so the huge size, you may say that, okay, memory is not a constraint. I can buy so many disks and fill up here and let the model run here and make a prediction. But there is a catch here. It's not about accommodating memory. It's about consuming less amount of power. So keep in mind that we have to address this challenge. We are supposed to optimize our neural network. And why we can't just say that it's only the storage. Storage actually generates a problem here. Just look at here. This is some statistics published saying that somebody experimented 45 nanometer at 0.9 volt, and they observed that these operations. So you can see here there are two kinds of operation. One is there are arithmetic operations. The other is data transfer operations. So this is an arithmetic operation. 32-bit integer addition. This takes 0.1 picojoules. This is taken as a reference here. If you want to do, instead of 32-bit addition, if you want to do floating, then it takes 9 times power. If it is a registered file, so we have a CPU, within that you have a register file, the register bank. Between registers, if you want to transfer, taking the content to the bus, it just takes 1 picojoule. Still it is 10 times more. But think that if I don't have the data in register file, but it is having somewhere in the cache or RAM, then the power consumption is 640 picojoules. So if I'm transferring from register, it is 1, but if I'm transferring from DRAM, it is 640 picojoules. So you can see here, multiplication of this is almost like 20x times more. So now we say that go back here, and if you say that I can store it in DRAM, whatever the memory size, let it be terabytes, that's not a smart thing, because for every operation you'll be spending 640 picojoules. So you can't justify saying that I can purchase something and do it. It's energy which is costing you. And what costs energy is data transfer.
So the seniors are calling Aditya for tech time.
Now, like, given this context, like we are deciding like how do you optimize neural networks? Yeah, neural means neural network. What are the choices? I just listed here some of the choice. So this is, you take a full network, train it, and then try to prune it. So take away some of the connections which are not important. This could save your memory if you cleverly do it, not at random. This is one of the choice. Other is why I want to always represent my data in 32-bit? Why should it be floating point? I can just reduce it. Maybe instead of 32-bit, I can use only 4 bits or 5 bits or 8 bits. So if I do that, the memory size is going to reduce. So it's an advantage.